We are ready here. My name is Jonas Karlsson. I work here at Google, and I used to do my PhD a number of years ago in Amsterdam. Here's my professor, Martin Kersten, who has been doing databases for quite a while and done a lot of interesting things. And the specialization is in main memory database system and data mining and highly efficient processing of slicing and dicing. And today we have two speakers, one at 1 o'clock and one at 2 o'clock. And first we're going to see Stratos Idreos, who is currently a PhD student at Amsterdam. And he's working on self-organization of database systems in terms of data structures and how to autonomously make the database handle partitioning and indexing without any user need to specify how to do this thing. Previously, he was studying the systems group in Crete, doing P2P databases. And today he's going to talk about database cracking. And hope you will enjoy it. Thank you.
OK, thanks. So hi, I'm Stratos. Yep. This is a joint work with Martin, who's over here, and Stefan Mangold, my advisors in Amsterdam. So this is database cracking. And you will hear about self-organization in database systems. The problem we're looking into is dynamic environments. So environments where query and data workload is continuously changing. You continuously get new data, different data, new queries, different queries. So there we have some hard questions to answer, some hard decisions to take, like what kind of indices do we use if you want to improve data access? When do we create an index? When do we drop an index if it's not useful anymore? And on which part of the data do we create indices? Because if the query workload is continuously changing, different parts of the data are becoming interesting at different times. So typically, we have database experts that monitor the system, or more recently, some special tools that try to recognize behaviors, patterns in the workload, and give advice, make predictions, make assumptions. You can imagine that this is a more hard problem in databases with huge data sets, because there, for example, the cost to create an index is even higher, or the cost of answering a query without the proper index is again higher. So what we're trying to do is give a self-organized flavor to the database. We want the database to be able to adapt itself to query and data workload. The basic idea that we're using is called database cracking, and it's like this. Each query triggers physical reorganization of a database so that the next queries can be answered faster. And what we have done so far is that we designed and implemented the system that proves this case by using database cracking and be able to show a clear self-organized behavior. We work on top of MonetDB. MonetDB is a system that we developed, it's a WI database system, and one of its characteristics is that it's a column-oriented database, which means that attributes in the database are represented as columns. So we'll see examples. So with this simple example, I will try to give you the basic concepts of database cracking. So assume an attribute in a database represented as a column, and a simple range query. So let's see how the cracking DBMS will answer this query. It will try to partition the column such as the result is in a contiguous space. So first we have all the tuples with values lower than that of the result. So you see values 3, 4, 2 that are outside the result for this query. Then we get the actual values that are in the result, and finally tuples with values that are higher than that of the result. So what we have now is 3 partitions. In the middle we have our result, and observe the following. Within each piece, there is no specific order. So, for example, in the first partition, you see we have values 3, 4, 2. There's no order there. But the pieces themselves are ordered. So, for example, every tuple in the first piece has a value lower, which is lower than every tuple of the second piece or the third piece, and so on. And this is the property that we can heavily explore to improve data access for the future. assume a query, for example, that requests values lower or equal to 5, then we can just go and search in the first piece, in the blue piece. So you can imagine that this is a pretty useful thing when it comes, especially when it comes to huge databases. This self-organization, this reorganization step continues with every query. So let's see what happens with the next query. You can see that this query requests everything between 2 and 15. If you observe now the column on the left, you will see that this query needs to analyze the first and the third piece. The middle piece is for sure within the result. We know that. So what the cracking DBMS will do is that it will further partition the first piece into 2 new pieces. So we get a new blue piece and a new green piece. And observe that the green piece is now within the result. The blue is outside. We get the orange piece. We don't have to analyze, think about that. And similarly, the last piece is further partitioned into 2 new pieces. So what we have now is, again, the result is in a contiguous space, but this time it's a collection of pieces. And what is the main observation from this second step that we did is that the more we crack, the more we learn. The more we physically reorganize the column based on what the users want, the better we can answer future queries. And this is exactly what gives us this self-organized flavor in the system. Now, you may wonder how this compares to some different strategies like sorting or indices. So since we are giving this order in the column, why not immediately sort the column and then use binary search, which is pretty fast? And the answer is that, yeah, you can do that if you have the time, if you have the resources, and if you know which attributes you want to sort. If you have this luxury, go ahead and use sort. Or go ahead and use other indices if you know how you want to prepare the data. So this strategy is for completely dynamic environments with completely no knowledge about what is going to happen. We have 2 cracking algorithms, 2 algorithms that physically reorganize columns, and that's all we need. So as you saw in the previous example, if you remember, we had one algorithm that splits a piece into 2 new pieces, and one algorithm that splits a piece into 3 new pieces. And that's all we need. We implemented various different strategies for these things, but at the end we ended up with some simple, with the most simple algorithms, which were very easily to implement very efficiently. And the main idea is that we read the piece, we read tuples using pointers from 2 directions, and we try to exchange tuples to get them in the proper position. And the whole effort is in exchanging as less tuples as possible and reading as less tuples as possible, ideally once per tuple. Now in this slide you can see the basic design that we have on top of MongoDB. Such like this. The first time that a query needs to touch a column, needs to touch an attribute, the system will make a copy of this column. This copy, we call it the cracker column of the given attribute. And then, each time a query needs to touch the specific attribute, we physically reorganize the column, such as the result is in a contiguous space, as we saw in the examples before. For each column, for each cracker column, there is a cracker index, which is an available tree in the current implementation, and helps us navigate very fast through the various pieces of the cracker column. Now, when we wanted to create the first query plans for cracking, the select operator was the select operator is the one that first touches tuples. So this was the operator where we went and plugged in physical reorganization. For example, the simple select operator, the naive select operator, simply scans a column and tries to find the correct values for a query. The new select operator that we created for cracking, it will first search the cracker index, reorganize any pieces that it finds, update the index, and then return a contiguous area as the result. And now let's see how this behaves. So here's an experiment where we have a column of 10 million tuples, and we fire 100,000 range queries. In the x-axis, you can see the series of queries. In the y-axis, you can see the cumulative cost after each query has been executed, and it's logarithmic. So the red curve is showing the scan select, and this, of course, it scales linearly. Then the green curve shows the sorting strategy, which is sort the column up front and then do binary search. So you see that we have a high initial cost, but then the curve is almost flat. So queries can be answered pretty fast, and if I remember correctly, it was in the order of a few microseconds. Then we have the blue curve, which is cracking. And now you can see that we don't have such a high initial cost. We don't have to invest. And also observe that the more queries we answer, the more flat the curve becomes. So queries can be answered faster and faster all the time. And the reason you can see in the right graph, where you see the amount of tuples that the cracking queries have to touch each time. And you see that this thing is coming down all the time. And that's because cracking learns and continuously restricts data access. Now, here you can see how cracking scales compared to sorting. So it's the same experiment as before. And here you can see for 20 million tuple and for 40 million tuple, what's the difference. And you can see that cracking is better compared to sorting, and that's explained because of the complexity. Sorting is an end log n operation. Cracking simply depends on the amount of tuples that we touch every time. This experiment is in-memory experiments. Tuples contain integers, but we expect that out-of-memory experiments should be better for cracking again, because we can simply use a recursive behavior to handle out-of-memory experiments. And here you can see an experiment where we use the previous experiments were just we're simply comparing operators. Here you can see an experiment where we're using the complete software stack and we're answering a full query. So TPCH is a standard database benchmark. The query 6 is a query that selects from a table using ranges from 3 different attributes, and then it projects some other attributes. And we compare cracking with some standard well-known database systems like PostgreSQL, MySQL, also using indices on the attributes that are used in this query. Also, you can see the green line, which is MongoDB, standard MongoDB, and you can see the gray line, which is cracking, that it is way below. And the observation is that if you see what happens to the first query, is a little bit slower than the green line, but then it quickly goes down, it learns, and quickly goes down, and performance is almost 1 order of magnitude faster. The last line that it's even more faster. It's another system that we're building at CWI, MongoDB X100, and Sander will talk about that in the next talk. But this one is using prepared data. So we have done some preparation on the data, which is not visible as a cost. So this is sort of the ideal cost that you can get if you know what you expect from your queries. And now I'm going to give you a little bit a flavor of how you can use updates in this architecture, so that I will show you that it's not something that it only improves query processing, but it also improves query processing during updates. So we have 2 structures, the cracker column and the cracker index, and that's what we have to update. And we're going to do that in a self-organized way, so again without external administration, without any database experts helping us, without any knowledge about the workload, the query workload and the data workload. So we have two issues, when to do that and how to do that. Answering the when question, we will do that during query processing. So like we plugged in physical reorganization in query processing, we plug in updates in query processing. So when an update arrives, it is not executed. It's staying aside in separate columns for each attribute, and it will be merged in the cracker columns only when a query needs that. So we made a new version of the select operator that before performing the physical reorganization step and the selection, it first updates the cracker column if needed with the requested values. Now, this shows you what is the goal. So in the left part, you can see a typical example of how a cracker column could be. And assuming you want to insert a new tuple with a value 9, and you can see that in the right part we went and we plugged in value 9 in the first partition, which meant that we also had to change to shift down the other two partitions. So how can we do that efficiently? We have a technique that's called hopping. It's a pretty simple thing, and it works as follows. We take from the last partition one value, and we put it one tuple, and we put it at the end of the column. So we made space in the column for the new tuple. We update our index, of course, and we do the same until we reach the partition where we actually want to put the new tuple. So now there is space for value 9, for tuple with value 9, and we just put it there. So we didn't shift tuples all the way down to the column and everything. We just rearranged a few tuples in the column, which is a pretty cheap operation compared to just shifting everything down. Now, we have a bunch of different strategies. One idea is that when a query needs some of the pending updates, we just go and merge everything. Another idea is that we just merge the tuples with values that qualify for the current query. Then there is the REPL that is trying to do exactly what is needed for the current query and nothing more. And you will see a similar example in the next slide. Another idea is that since all this are auxiliary data structures, we can just throw away the cracker index, update the cracker column, and then start the whole procedure from scratch, or just partially delete the index. So here you can see the REPL. So on the right, you see the assume pending insertions, and on the left, an instance of a cracker column, and the query that wants to select everything between 7 and 14. From the pending insertions, you see that tuple with value 9 qualifies for this query. So we need to insert in the cracker column the value 9. We make room just a bit after the first partition where value 9 should be inserted. So we take the tuple with value 18 out. We put 9 there. 18 is going back as a pending insertion, and the cracker column is updated, and the cracker index is updated. And here you can see that this is even faster compared to the previous algorithm that I showed you. Now, this, I hope, will give you an impression of how the different strategies behave in the baseline. So starting from the top left corner, you can see the scan select. That's an experiment where you have a 10 million tuple, a 10 million column, sorry, and 10,000 completely random queries that select 10,000 tuples every time. And every 1,000 queries, we have 1,000 insertions. So the red line is the scan select, continuously scan the column to get an answer. The green line, just the graph below, is representing the cost of having an AVL tree on top of a column. So you can see that this is pretty cheaper with just a few small peaks when inserting new values. Then the blue line is representing this delete strategy that I told you before, where you continuously, when you have new values, you delete the cracker index and you start building again. So you see a behavior where we have some peaks and then we quickly learn again and learn again and learn again. And on the right side, you can see the merge strategies that they try to merge into the cracker column the new values. So first, on the top right corner, you see the strategy that completely, that when even a single value is needed from the pending updates, it just merges everything into the cracker column. So you see that response time is continuously very low. At first is a little bit bigger, but then it learns, and then it's very low, and we just have some peaks when we actually have the insertions. So if you see then the next figure, what we improved, which represents the gradual case, so merge only what is needed every time. What we improved is that we don't have these high peaks. So we improved the average response time. But as you can imagine, by looking both graphs, at the end, the cumulative cost for the gradual case is a bit higher. And there we have for that we have the ripple strategy, which is at the end, where the difference is that we always touch what is needed. And if you remember, we had, for example, to insert one value, we just do one operation, one shifting. And that's why you get this very high performance without peaks, without nothing. So that's the basic performance you get from these algorithms. So database cracking may sound like, at first, like a crazy idea, because nobody would think that it's very reasonable to physically organize the database while answering queries. But this system shows that it has some potential. It clearly shows some self-organized behavior. You can restrict data access. And there is a bunch of research opportunities for cracking. For example, there's, of course, a lot of optimization questions. Cracking can be explored in more operators like join queries, aggregate queries in databases. You can have cracking histograms. You can use distributed cracking. So you can imagine that if you have partitions in the database that are needed for different queries, we can just throw the different partitions into different CPUs, different nodes, and so on. And we had a paper which we presented in 3 days ago, in CIDR 2007 in Asilomar. So you can go ahead and download it and read this paper if you like. So that's it. Thanks.
Thank you. So we open the floor to questions. So does anyone have any questions?
No? You can use this one.
So now we open the floor to questions. So is there any questions here? Feel free to ask, and the speaker will be available afterwards also.
You?
I'm wondering, with updates, you swap these values and put in, now you put in into the spot of 18 in your example.
Yeah.
And do you also sometimes, when do you flush pending updates
Repeat the question.
Yeah, so Sandro is asking if at some point in the ripple strategy that I showed, if there is a point where we can just merge everything directly into the cracker column. That's what you're asking?
Yeah,
well, the answer, I think, is that if you detect that there is idle time, no queries, no updates, then of course you can do that. Yeah.
scale to the Google scale?
We'll see. We hope.
So I have a question about when you, after a while, when you start cracking a lot and you have a lot of queries, suddenly each value will be its own element, its own partition, right? So how efficient is that in storage-wise, and the AVL tree you need to access all these parts?
Yeah, yes. So you can see the first bullet here, which says that this is future work. So the intuition is that we won't let that happen. We won't let that having such small pieces. Ideally, a piece could be a cache line size, the size of a cache line, so that you can efficiently read each piece. And of course, there are trade-offs there. That needs to be studied. Please. Mm-hmm. Okay, the question is how well does it scale? I don't know if you were here. I saw this graph that shows how well it scales within memory. So you can see a 10, a 20, and a 40 million column. And it is compared with sorting. So you see that it scales pretty well compared to sorting. So you see the 10 million curves, they meet after 100,000 queries, but then they have a distance, they have a gap. But outside of memory, yes, yes.
So part of my question is about when you have more concurrency. When you
Okay.
And you have, say, a wider table with multiple columns and a big
Well,
mix of
multiple columns is not an issue because this is a per column operation. So multiple columns is not an issue, but within each column, if you have concurrency, if you have multiple clients, then the idea is that you will lock the select operator that performs the physical reorganization, and you will lock it in terms of the cracker index. So if you are accessing the same area, the same piece, then you will lock this piece. But if you're accessing different parts of the column, you can reorganize it.
Okay. All right. Any more questions? The speaker will be available in this area. And 2 o'clock, we are meeting Sander Herman, and he's going to talk about running database system on modern hardware. So he's taking into account cache lines and how to optimize for CPU usage, because nowadays we know that the main memory is actually a bottleneck compared to the CPU's ability to process data. And he's going to talk about compression for superscalar CPUs. All right, thank you very much.
Thanks.